I guess this is visible now.
Yes, very good. Thank you.
Good afternoon, everyone. Jyotirmoy, I think we need to wait for another 5 minutes.
Yes, no problem. Shantanu, thank you very much for sending the reminder today.
No, it was our duty, right?
I almost forgot about it. Yes.
No, nothing. Yesterday, people were really busy with two things. One is storm, another one is another storm, KKR versus Hyderabad. So people might forget. Okay.
I am currently not in my regular working place, so that's why I kind of lost track of time and everything. So thank you very much.
So you were not in Bhopal or you were in somewhere else?
No, I am not in India.
Okay.
Yeah,
Where
So
are
it's-
you?
I am in Saudi now. Saudi.
Oh,
Oust.
okay. For work or for trip?
No, for what? For 3 months I'll be here till July end.
I think Jyotirmoy is now in India, right?
Yeah,
Are you
I'm in India. Yeah, last few weeks actually.
Otherwise, because I see that you have some sunlight in your room. I think.
Yeah, I'm in my room actually. At least one Jyotirmoy is in India. Yeah.
Thank God for that. Otherwise, India will be unstable without all the Jyotirmoys. Yeah. Thank you, Nilanjan.
Thank you.
Okay, I think we should start
I
now.
think. Yeah. Let us start,
Okay.
and I think.
Yeah. All right. Thank you very much, everyone, for joining in today. And today we have Dr. Jyotirmoy Pal with us, and I'll briefly introduce the speaker, and then the talk will start. So Jyotirmoy obtained his bachelor's and master's degree in geology from Jadavpur University, and then PhD from IISc Bangalore. And then I think till now he was a postdoctoral fellow at University of Bayreuth in Germany. And he will be joining soon the Center of Planetary Habitability at the University of Oslo as a Marie Curie postdoctoral fellow. So he has been working on solid earth geophysics, and today Jyotirmoy will be delivering a talk entitled Understanding the Stability and Evolution of Continental Cratons, Insights from Numerical Modeling. So with this brief introduction, may I invite Dr. Jyotirmoy Pal to deliver his lecture. Over to you, Jyotirmoy.
Yeah. Thank you. Thank you for such a nice introduction. I hope you can hear me. So I'll be talking about the craton evolution today. So this work was started when I joined as a PhD student in IISc, and then I have been doing this work for now almost a decade, different aspects of craton. So these are some of my collaborators who have worked with me since my PhD days and still collaborating. So I should mention their names as well. That's why I kept their names. So first of all, I'll briefly discuss about my research interest, which has already been discussed, but still I would give a bit more emphasis on this word geodynamics. So I do geodynamics, which is a branch of solid earth geophysics, and dynamics is essentially a word that involves the force calculation. So often people just very lucidly use this word geodynamics, but traditionally geodynamics is something where we calculate the forces within the earth. And using this tool of geodynamics, I actually work on two different kinds of problem. One is the geodynamics of the craton, which I'll be focusing on today. And you will understand that this is considered as one of the grand challenges in geodynamics. And another work that I've started doing during my postdoc is the grain size evolution and how that mineral grains can actually affect the mantle dynamics. But today I will not be going into the grain size evolution part, but I'll be mostly restricted within the geodynamics of the craton. So in the first part, I'll give you a very brief introduction about the craton, which is the core part of today's talk. So I have given this craton talk in different parts in different universities, but I always came back to thought like, how should I introduce the craton? So I thought this time I'll do something different. So I am showing the earthquake zones in India. So here you can see that India, this is the map of India, and it's this red colors or blue colors. These are the different zones of earthquake, where you can see this Himalayan region or this plate boundary region near Gujarat. These are marked by red, so they are very much prone to earthquake. But if you see these cold blue colors, these are almost devoid of any earthquake. And we call this as the stable continents. And we probably know all of them, these names, this Marwar, Bundelkhand, Shingbung, Basta, Dharwar. So these are called the cratons. So all of this unit make one Indian craton. Now, if we go back to the world map, and we'll see this kind of stable continental interior is present all over the world. And these are marked by these red lines, which is the Archean basements. And these are called the cratons. So they have some specific characters. One character is they have a very thick lithosphere. Well, generally lithosphere is 100 kilometer thick, but these cratonic lithospheres are more than 200 kilometers thick. And then we have the very special characters of these cratons that they have suffered very less deformation, particularly after the Cambrian. And they're mostly made up of felsic rocks. Another point is that the cratons are surviving since Archean. And Archean is a time which is around 3.5 to 2.5. But why it is surprising to have such older rocks on the Earth's surface? So the answer is the plate tectonics. Because Earth is a planet where the active plate tectonics goes on. And if we see this ocean floor age map, so these colors are representing different age, we'll see that oceans are not older than 300 million years. In the counterpart, if we see the continents, we'll see that most of the continents are around 1.2 to 1.6 billion years. Only there are some these blue patches, which are the cratons, are surviving for more than 3 to 3.5 billion years. So this is quite surprising, because plate tectonic tends to destroy lithosphere. That's why the older lithosphere is destroyed and newer are formed. But somehow these cratons have survived for unusually longer time. So one can think that maybe some few rocks in the Archean were formed and they have somehow escaped the destruction process. And that's why they're born with a golden spoon. But is it so? I think the geochemistry will say a different story. So this is one of the very famous curve of continental crustal volume. So this curve shows that how the continental crust have evolved with time. The time axis is the x, and the crustal volume is the y-axis. 0 represents the present day, and in the rightmost corner you have the 4.6 billion years. So these top three curves, this blue, yellow, and green, shows how the continents have evolved over the time. So if we see around 3 to 3.5 in this time, there are at least 50 to 70% of the present-day continental crust are already present. And this red line, which represents the age of the crust that is preserved today, and we see that only 5 to 10% of them are preserved. So it is quite curious to know that there were huge volume of continents that formed at that time, but most of them got destroyed. But only this 5 to 10% of the rocks have survived somehow. So they should have some special character, and we are interested to know that why they have survived for such a long time. So this was the scientific part, scientific question I want to address. But there are other aspects of the craton. So I'll give a brief overview, like why the other disciplines of the geoscience should also care about the craton. The first is the Archean geodynamics, of course. So one of the most interesting questions for us, for geoscientists, that when did plate tectonics start? So we probably now know by this time that Earth goes on a plate tectonic kind of setup. But in the earlier, this tectonic setup was not there. So plate tectonics is a kind of a process where subduction zones are the dominant mechanism of this tectonism. But in the earlier, there could be a stagnant lid. That means the lithosphere is not interacting much with the mantle. It is more passive. Or there could be squishy plume lid kind of setup where there are small ridges, but there is no active subduction. There are several other mechanisms which has also been proposed nowadays, but lid or from squishy plume lid, it has transitioned into plate tectonics at certain point of time. We do not know when and how. If we want to address this question, the only thing that we have in our hand is some rock samples from the cratons, because whatever chemical or physical changes Earth have experienced at that time are all preserved within the craton. So if we study craton, this question might be addressed at some point of time. Well, nowadays craton is getting more and more importance because its relation to the origin of life, because it has been proved that the Archean Earth was submerged under the water. Now, as these older continents or the cratons started to rise above the sea level, they created a shallow marine condition like this. And these are the locations where there could be more nutrients, the oxygen levels can be different, and these are the potential regions where the life can be harbored. Also, when they started to get up above the sea level, started weathering. And because these rocks are silicate, when the weathering starts, they draw down the carbon dioxide from the atmosphere, and that could have impacted the global climate and could have probably contributed to the great oxygenation event at 2.5. So apart from this scientific interest, Craton has a very important aspect economically too. So the world's all the diamonds are found within this Cratonic region. Apart from the diamonds, Cratons are also repository of several valuable ore minerals. So if we see in the great picture, the broad picture of the Craton, that is quite interesting, and that could be relevant not only to the solid geophysics people, but different aspects like ore geology or core geology. So it's a vast topic. But today I'll be talking mostly on why they're stable on this earth. So I use a tool that is called numerical modeling. I give a very basic idea what is a modeling. So in this part, if it was a in-person talk, I generally ask audience like what is a model, but I guess I have to skip that. So I have written what is the model. It's a representation of a system of ideas or events or process. Now this may not be very clear, so let us see some figures that will be more interesting. So this is the reality, this is the real heart, and this is a real earth. It looks like that. Now if we want to make some representation of this, in a very simple case, we can make the heart like this and the earth like this. This is the most simple. Now if we gradually increase the complexity, then we can probably make something like this. And if we add some more complexity, then the model will look like this too. So from simple to complex, we can generate different models. But one thing you should realize that the models never becomes the truth. It is some kind of assumption, and we need to understand what is the best model in that scenario. So how do we produce this kind of models? It looks like nice pictures, but what is going behind these pictures? What is going behind the pictures are some mathematical equations. So if we are doing the modeling for the mantle convection, we need to know three equations. There are only three equations, and these are the conservation of mass. This is simply that mass change over the time, and the input and output flux of the mass in a system should be constant. The second equation is the conservation of the momentum equation, which is the body force and the surface force should be in equilibrium. This is called also, in a different format, this is also called the Navier-Stokes equation. And this is the conservation of energy. This is nothing but the diffusion and advection of temperature. Instead of temperature, this could be also compositional. So we need to solve these equations to develop our modeling. So from this weird mathematical formulations, probably you have already recognized that these are partial differential equation, and I will tell that these are also nonlinear partial differential equations. So this cannot be solved analytically. It's not like some dy dx equal to 2x and you just integrate it and find y equal to x square. It's not like that. It's much more difficult than this. So that's why we need to use numerical techniques. So what are these numerical techniques? I'll just give a very simple example so that you might be understanding that what is the process actually. So if we take one very simple equation dy dx equal to fx, we can write this dy dx into this form y2 minus y1 divided by x2 minus x1. So this is called the discretization, and this is coming from the first principle of differential calculus. And now once we have discretized this equation, we can simply write like this. So just replacing this x2 minus x1 as del h, which is called the step size. And then we can solve for y2 and x2, and this is called the linearization. So these two are the main thing of a numerical modeling, discretization and then linearization. Well, depending on which technique you are using, there can be additional steps. I'm not going into that, but this is the fundamental of understanding the numerical methods. So I can give you an example. So let us take this very simple example of if the function is 2x, then probably you can analytically solve it, that y equals to x square, and the numerical solution will be something like this, exactly putting this form: y2 is equals to y1 plus here fx equal to 2x, so 2x into del h. Now if we plot and see how this two solutions differ from each other, so we'll see some interesting thing. So this blue line is the analytical solution. So this is the truth. It's like the absolute truth of this equation. Now, if I solve it numerically with a step size of 2.0, I will find a curve something like this, which is this YOLO curve. Now you can see there is a significant amount of error in this. The beauty of numerical modeling is this, that you can reduce this error. So in this case, if I reduce the step size to 0.2, then this new red line is added. You can see that it is almost similar to the analytical solution. So there are several techniques by which we can reduce the error. We can go close as much as possible to the reality, but still we end up with some error. So that's why we need to optimize the model and interpret the best possible scenario. Okay. So what happens for the Earth? How do we solve those big equations for Earth? So if this is a spherical Earth, as I said, the first step is the discretization. So we discretize these equations in these different nodes and solve for them. So this is one of the models that I use. This is a finite element model, which is slightly different than what I've given as example, because this is more in-depth and more details, more complicated model. But the idea remains the same. First, you have to discretize this, and then you have to make some linear equations by which you can solve those mathematical equations. As an input, we give some parameters like density or buoyancy or temperature or velocity boundary conditions that will drive the mantle convection within Earth. And also, okay, so how to see that? So this is kind of a density or temperature anomaly. So in our model, you can see like we have this African plume is something like this. The continental interiors are mostly very cold, that's why they're blue. And there's a thermal anomaly in the mid-ocean degrees. So this kind of 3D structure we can actually incorporate in our model to develop, to get the results actually. And we also incorporate some rheological parameters. And these rheological parameters give us the value of the stress, which is very important in our case. So this was the basic of the numerical models. Now I'll come to the main issue of this talk. Maybe I take 5 seconds so that you can bring back, maybe if someone is lost in the talk. So this talk is on, again, stability of the craton. So I'm interested to know that why the stable cratons are there on the Earth, even if it is tectonically active. Okay, so the first part, what makes the lithosphere stable? So if we have some craton like this blue region is a craton, and the mantle is flowing beneath it, and mantle always exerts a shear at the base of the craton, or any lithosphere actually. And if it is thick, it can produce this kind of lithospheric drips, which is kind of similar to Rayleigh-Taylor instability or gravity instability. And then this part of the craton can be destroyed. This is the process called delamination or destruction. So how can we stop this destruction? This is a phenomenal paper in 1975 by Thomas Jordan, which is the hypothesis of continental tectosphere, where he has proposed that cratons are made up of lighter elements, or they're neutrally buoyant. That kind of agrees with the geological records, because these rocks are felsic rocks or granitic rocks, which are naturally neutrally buoyant compared to basalt or peridotite. So this was a theoretical assumption, and it looked very well, but it was never put into test. So in 1999, at the dawn of numerical modeling, this theory was tested by Leonardi and Moresi. So at that time, the numerical models were really, really simple. So they have a box kind of setup. They have a circulation motion, which simulates the mantle. And they have put a block kind of this black box kind of thing, which is representing the craton here. And they simulate how the cratons are getting deformed with time. In this case, the craton is neutrally buoyant. And as you can see, this time is going on. These are some relative time scale, which is not important, but just to see the steps. So what you see that the cratons, even if they are neutrally buoyant, they are actually getting mixed within the mantle. So only a neutrally buoyant may not be able to resist this mantle shearing. So they are bound to get destroyed. So then Leonarding and Morrissey thought that there has to be something else other than the buoyancy, and that could be the material strength or the viscosity. So in the second model, they have kept everything same, just now they have made this block 50 times more viscous than the previous. And you can see the result. Now the time step is more. However, the craton is less deformed. So this idea actually was revolutionary, that craton has to be more viscous compared to its surroundings. And what I try to do is to estimate what should be the viscosity of the craton that makes them stable for billions of years. So that is the key aspect of my model, the lithospheric deformation. So whenever the mantle flows underneath any lithosphere, and lithosphere have a variable thickness, where this is the mid-ocean ridge kind of setting, it is the thinnest part and the craton is the thickest part, it exerts stress, and stress is a tensor. Now if we take the horizontal component of the stress, we get a vector that is called the basal traction, and which is represented by this formula. This is actually quite simple to understand. This is horizontal strain rate, just written in a polar coordinate form, and multiplied by the viscosity that gives me the stress. And all these velocities are obtained from the numerical model. So that's how we develop what is the stress and strain underneath the lithosphere. And we see that how this lithosphere is deformed because of its thickness and viscosity. Well, this looks a complicated figure, so I'll ask for more attention. I'm describing everything in this figure. So this is the output of our model. This background color, which is represented by this scale, is the viscosity. So 1 means 10 to the power 21, and this is in a log scale. So if you go in a negative direction, that means 0 is 10 to the power 20, 2 means 10 to the power 22. So there's a variation of viscosity. So this lighter color indicates somewhere near the mid-oceanic ridges. So you can see Atlantic and Pacific is a bit lighter in color. The continental interior is slightly viscous. And well, there is no high viscosity craton in this particular model. That's why you don't see any. Okay, the next one is the arrows. These arrows are the traction vectors, which are described in this slide. So this is the magnitude, you can get it from here. And if you do a tan inverse of it, you will get the direction of the traction vectors. In this particular model, where there is no craton, the traction vectors are more or less uniform within around 5 megapascal. And there is this focal mechanism kind of thing. This is a beach ball kind of thing. This has a meaning to stress. So the scaling is given here for these balls. And you see, if this value is negative or brownish in color, then it represents a compressive region. We can test quickly, like if you see this Himalayan region, then we can find that these are, of course, compressive stress. If we come to the Andes region, we find again these compressions. But if we go to the East Pacific Ridge, so this is showing blue colors or positive value, that means it's extension. Same thing happens for Atlantic Ridge also. So it looks fine. So now if we incorporate cratons in this model, something interesting will happen. So now we can readily identify that cratons are marked by these dark colors, which represent a very high viscosity, around 100 times more viscous than their surroundings. And the tractions have increased. So you can see the traction vectors within the cratons are very, very high now. And also most of the cratonic interior is now becoming brown. That means they are within the compressive stress. if I just zoom into one craton, here the patterns are more easily visible. So what we see that the tractions are inwardly convergent towards the craton, and we see all over the craton there is a compressive environment. So we call this as a convective self-compression. So this is a key feature that we have identified within all the cratons that are within the compressive regime, and this compressive regime can protect the cratons against the disintegrative forces of mantle convection. So this is one of our key findings, that why the cratons can be stable for such time, because they can literally oppose the disintegrative forces of mantle convection. So now this was the calculation of the direction of the forces. What about the magnitude? So here we plot the basal traction magnitudes in the y-axis, and the x-axis the lithospheric thickness. These lines are coming from different models. I'm not going which model is what, but one thing you can appreciate, that whenever there is a thick lithosphere, the traction is increasing. That means the cratons, which is the thickest lithosphere, have the maximum stress. If I see the corresponding strain rate, that looks a little bit surprising, because now this strain rate completely opposite. Okay, so why that happens? Because it seems like it is counteracting with the Hooke's law that says the stress is proportional to the strain rate. But this Hooke's law is only applicable when you have a constant viscosity. But in Earth, if you realize that the thinnest lithospheres are the mid-oceanic ridges, which is the least viscosity, and the cratons are the thickest lithosphere, they have the highest viscosity. So because of this viscosity and thickness, they can actually resist against very high traction also. So this thickness and viscosity are the key to slow down their deformation at the base, so they do not get entrained by the mantle convection forces. But we're talking about the viscosity qualitatively, it has to be higher viscosity, but how high is the high? So that's why we develop this kind of time-dependent models. So what we do here, that we first reconstruct the craton's location back in time. So in this case, we have got the cratons when they were at 410 million years ago. So these were the rough locations of the cratons. You can see these cratons are marked by these slightly highly viscous regions. And now we simulate the model and come to the forward direction towards the present day and see how the cratons are deforming. So in this particular model, we have a craton viscosity of 10 to the power 20 to 21, and we have also an asthenospheric viscosity of 10 to the power 10 of 19, and see how this works. Well, so you can see the cratons are deforming very quickly in this setup. They're all getting mixed up. Yeah, almost every craton got destroyed. So there is no trace of the craton with this kind of viscosity. So this is kind of a normal viscosity of any lithosphere in a mantle. So this is not a sustainable viscosity for craton. Now we increase the viscosity of the craton to one order, 10 to the 21 to 22, and see what happens. Probably you can recognize that cratons are deforming a bit slowly. They're still here, but heavily deformed. Also, the smaller cratons like India or Australia, they're completely gone in this model. Now we increase the viscosity of the craton to around 10 to the 23 to 24, which is likely to be the magic number in our case. And we see that in this case, the cratons are not at all deforming. And all the shapes are being retained, and all the cratons are going to the exact location where they should be. So not only they have retained their shape, but also they have reached to the exact location where they are located. So this is kind of the viscosity that we estimate could be important for the cratons to survive for billions of years. So to take away message from this part is that self-compression enhances the craton stability. The viscosity and thickness resist the deformation against the mantle destruction forces, and the minimum viscosity of the craton should be around 10 to the power 23. So with the stability of the craton, many people started to think that cratons are immortal. But until recently, we are witnessing several cratons that might have undergone some kind of destruction. So this part is about the destruction of the cratons. How the cratons can be destroyed, there are several processes. If mantle plumes come under a craton, then they can thermally weaken some part, and this weaker part can be later removed. Or if there is some subduction is going on, they can release subducting fluids, and this fluid can hydro weaken the part of the craton, which again can be destroyed. So these are the two different scenarios, and we have witnessed these two different scenarios, one in India and one in the North China. So I'll talk about two different end members of craton destruction process. First, coming to North China. Those who are not very familiar with the North China geology, so let me introduce a little bit. This pink boundary is the craton boundary, which is divided into two parts, like Western Bloc, and this is the Eastern Bloc. And in the middle, we have this trans-North China origin. This is kind of the tectonic suture in India, where all cratons got amalgamated. This is kind of their tectonic suture. And if we see the seismic velocity anomaly, which is represented by this background color, we see that Western Bloc has a very high velocity anomaly. This is the typical characteristics of craton, because cratons are old and cold. That's why they have very high seismic velocity anomaly. But if we come to the eastern part, then we do not see any significant higher velocity. It's very low velocity rather. Also, this green contours are the lithospheric thickness contours, and we see that Western Bloc is still very thick, more than 210 kilometers, but the Eastern Bloc is very thin, it's close to 100 kilometers. So all this evidence suggests that the Eastern Bloc of the North China Craton got destroyed, extensively destroyed rather. And why it has been destroyed, there are several mechanisms. It is a very controversial topic. So we'll see some of them now. What are the mechanisms? So first of all, let us see some geochemistry again. So there is a line along this XY, and people have studied the igneous rock along these lines, and they have plotted their ages. So if we see the age trend of igneous rock along this line, this is the Y, and this direction is the X. So initially at around Triassic, late Triassic, the rocks, the igneous rocks that were forming, the volcanism that were forming, it was happening near the sea. And as we are going towards Jurassic, all the igneous rocks are moving towards the landward direction, towards the continental interior. And after Jurassic, all the igneous rocks start to form again towards the seaward side. So there is a kind of a magmatic reversal in this region, and this has been interpreted as the onset of the flat slab subduction. So when there is a subduction was going, and if the slab is flat, then it can first go into the landward direction, and in the second step, when it will roll back, then the volcanisms will be created towards the seaward side. So when the slabs release the fluid, it can weaken the craton, and which can be later destroyed. So we kind of use this previous geological setup in our numerical model. So this is a numerical model where we have set up this scenario. We have this teal colored flat slab, this grayish color craton, and this dark blue color eastern part of the craton, which we will make gradually weaken to simulate the hydro weakening process. There are other aspects also, like this is the upper mantle, this is the lower mantle, and so the second figure is showing the viscosity. So you can understand that the craton viscosity is very high, also the slab compared to the mantle viscosity, and we can see these velocities. Now we'll see what is happening as this blue part, the eastern part of the craton, gets weakened. So yeah, now this is a setup where the slab started to roll back, and we can see that, okay, these white lines are isotherm. This top one is the 1200 degree and the bottom one is 1400 degree. And we can see the craton is started to getting peeled by the subducting slab. And after that, yes, probably, yes, this is a scenario to address once more. So here you can see this forming lithospheric drips. So there are two mechanisms. One is the peeling off, and one is the formation of the lithospheric drips. That is destroying the craton very quickly if they're made weak. Sorry. So I'll complete the animation again. So and also I'd like to emphasize on the point that this craton destruction, this started from zero, and at the time of 28 million years, almost all the cratons are destroyed. So it took only close to 30 million years to destroy most part of the craton. So of course we can understand from this that the hydroweakening can destroy the craton very quickly. In contrary, there is another n-member scenario, which is the Indian craton scenario, and we have three plumes here acting, Kerguelen, Marion, and Reunion. But this Reunion plume is crucial because it erupted just beneath the India. So here we try to see how a plume can change the thickness of a craton. So we again do this kind of model where we first locate the craton where it was at 65 million years ago. We construct a plume-like structure beneath this craton. We keep the temperature of the plume at 1600 degrees centigrade. And to induce thermal weakening, we use this kind of Arrhenius kind of viscosity law, where the viscosity will reduce if the temperature is more. So if I see the result again for the Indian craton, so here is the viscosity map. This blue to yellow color is the Indian craton, and beneath that you can see this red colored plume. And if I run this animation, you can see that as this plume is erupting, it is kind of eroding this craton. The craton is getting quite thin now. Yeah. So you can probably appreciate that this craton is this much now, this much thinning. In the beginning, it was quite thick, and in the end, it ended up with such thinning. So if we see another model where there is no craton, just to compare, we don't see any thinning here. The craton remains as it is. Yeah, the craton thinning is not observed. So thermal weakening can also mechanically erode the craton, that can attribute to its destruction. But now if you want to compare how these two mechanisms act on the cratons, so to do that, we kind of estimate how much craton is destroyed at what time. So in the x-axis, we have the time, and in the y-axis, you have the substituted mantle, which is equivalent to the amount of craton destruction. And for North China, well, there are several lines. These are these lines from different models. Not going into the modeling details, which are, but just to appreciate that how fast it can get destroyed, you can say that most of the models, the craton destruction is only within 20 to 30 million years, and the destruction amount is around, actually more than 90% in many cases. But if we see the Indian craton, here the thinning is very slow. So only this blue line, this only one model shows a very significant destruction of about 75%, but it took around 65 million years to reach that amount of destruction. But the other models show that the maximum is like 50% to 20% destruction can happen in 65 million years. So if you compare there is a rapid destruction due to the hydro weakening, and the plume-induced weakening is much slower process. So if you want to take some message from this part is that cratons, of course, are not immortal, and the plume-induced craton destructions are quite slower compared to the hydration weakening, which is very fast and can destroy the cratons very quickly. Well, coming to the almost at the end of this discussion session is what I call as the balancing of craton thickness. Why do I call it? Just let me explain. So if we see the history of the craton, we'll find that most of the craton has undergone some destruction mechanisms, starting from the slave craton, bushveld, warming, Brazil, India. There are recorded destruction events in these cratons. So it means that most of the cratons have undergone some kind of destruction. The lithosphere do get thin, but still we find that cratons are around 200 to 300 kilometer thick, which is a key for their stability. So why do they maintain this kind of 200 to 300 kilometer equilibrium thickness? So we have a hypothesis. It says that whenever you place a craton within a convecting mantle, then because of its thickness and viscosity, it will divert the mantle flow. And this mantle flow will kind of start compressing within the craton. And this compression can form this kind of lithospheric drips that will one time, it will probably increase the thickness, but because these drips get weaker, then they will be again cut off from their base. And that's how this equilibrium thickness can be maintained. So this is one of the hypotheses. I'm not saying very strong words on this, because we have already seen that cratons are under compression. All the cratons are under compression. We have seen that. So that's why we thought this could be one of the mechanisms. But if they're feasible or not, we'll see in our next project actually. So this will be my next postdoc work, to see that why the cratons maintain this kind of 200 to 300 kilometer thickness over the time. So if we get some interesting result, we'll be glad to share it again with you all guys. So to conclude about my talk, well, there are several things, but I'll just highlight some important things. That self-compression or convective self-compression is the first thing that is significantly we found that these cratons can resist the mantle convection forces because they are in a compressive region. Also, their viscosity and thickness are the two key factors for resisting the mantle shearing, and this viscosity has to be at least 10 to the 23 Pascal second. However, cratons do get destroyed, and there are several procedures, but thermally weakened cratons get thinned very slowly, whereas metasomatically or hydration weakening can destroy the craton more catastrophically. So here I end my talk. So if you have any questions, I'll be glad to hear. Thank you.
Thank you, Jyotirmoy. Very nice talk. The floor is open for question and answer now. Please raise your hand and yes, and please go ahead.
Jyotirmoy, can you listen?
Yes.
Okay, so could you go back to the slides where you are showing some beach ball diagrams and that self-compressive regime? Yes, okay, so it was an excellent talk, but few things I missed out. Like for these are the results of your simulations?
Yes.
So I could not get, like you didn't show that what was the initial condition of your simulation. So it was hard to follow here. Like what were the boundary conditions you gave and what were those parameters?
Yeah, I did talk a little bit, but of course I didn't talk much in details because then it will be a very technical one. So boundary conditions here are free slip in the top. The density is given from a seismic tomography anomaly. So this kind of seismic tomography anomaly that the 3D model is showing.
Okay.
These two are the only input conditions. There is rest of the things are very much self-consistent.
Okay, another thing is that if you go again back to that slide, so yeah, these are like you are showing viscosity and stress. These are from surface or at some depth.
Oh yeah, good question. This is at 120-kilometer depth. I have I have the results from surface to 3,000 kilometer for whole mantle convection, but this particular figure is from 120-kilometer depth.
Okay, but at times you mentioned that the lithosphere is 200 kilometer thick even.
Uh, I don't know where did I mention the lithosphere is 200-kilometer thick.
Right. Okay, I think you mentioned right at the start that in general the lithosphere is 100 kilometer thick, but in Craton it can go up to 200
Yeah,
kilometer.
that's a general observation. But
Okay.
in this model, the cratons are 300-kilometer thick. We took the upper bound of the thickness.
Okay,
Yes.
300. So another
Yes.
question is that you explained this self compression just by the shear given by the mantle, right?
Sorry, I didn't get.
You explained the mechanism of this self compression, like in the last slide of yours, because
Yes.
of the traction, right, at the base of the lithosphere.
Yes. Yes.
Yes. So my question is that traction is given at which depth, if you can tell.
No, this is a 3D model. Every depth we have traction. This traction is again plotted at 120-kilometer depth. So it's not a slice. The model is a 3D global model. So,
Okay, okay, okay.
so every at any depth you will get some traction, some value. So yeah, this is not a thin sheet kind of model. So
Okay, okay. So, lastly, maybe not related to your topic, but can you show that slide where you showed that hydrolytic weakening is happening?
uh,
The numerical model, subduction.
yes,
You can show that slide, please.
yes.
Yes,
Here I
this one. So if you play the movie, like this is not related to your work, but at some places, if we see in the subducting plate, the velocity vectors are pointing upward. Why is that occurring?
uh, see this is called an H-driven convection.
No, I'm not talking about that part. In the upper in the right part of your model. Yes, yes, exactly. There, if you go towards the upper surface of that part and you play the video, at places the velocity vectors are pointing like upward. If you play the video,
Okay, I think yeah, I I think
okay,
I
you look
understand.
at the right part. Yes, yes, there, the red arrows.
Ah, sorry.
Yes, 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 there, right there. So why is it occurring that the subducting plate has an upward velocity component here?
This is not actually upward velocity. Well, this is just the representation. Because there is a corner flow around this. So if you this is just a circulation. This is definitely not going beyond the domain. So this is slightly an effect of because in this region there will be some kind of upliftment also. So
Yes.
that will change the velocity towards slightly towards the upper side. That's very normal because you can see this there is a circulation. Two circulations are going on, one in this end and one is in this end. So
But
there
as much as we know that circulation actually generates traction at the base of the lithosphere, not at the upper surface of the lithosphere, right?
no, this is not the traction, this is velocity.
Yes, but it is occurring at the upper part, it is projecting upward. So,
It's not really projecting
like
upward.
it is also neutral buoyancy is there also. So that also will create a downward component, but it is still showing upward. That's why I am worried about.
Well, I find it normal because there is a circulating motion and some part will, because there is an upward movement, it is very normal to have this kind of velocity.
At the upper crust also.
Yes, because it will uplift. No, this is a free surface model. So if something uplifts, your crust has to have an upward movement.
No, generally what I see in the models is that this circulation gives rise to a traction below the lithosphere. So this velocity does not go beyond the lithosphere, like in the general models.
So maybe we can talk in details.
Yes, yes. I think one of the reason can be that your resolution is low. That's why we are getting
So
this.
these are very high resolution models. These are not resolution.
Okay, okay.
So,
Okay.
yeah, you can write to me if you want to
Yes.
discuss.
No problem. Thank you.
Yeah. Thank you for your questions.
Thank you, Ayan. Any more questions? Yes, sir. Neptune, sir, go ahead, please. We can't hear you. Perhaps you are muted. Neptune, sir, please
Yes.
go ahead. Yeah.
Can you hear me now?
Yes.
Yes.
Okay. So I very nice talk, great talk, and makes one thinking and wondering about geological processes. So one questions I had was, so the model that you presented, what will be the geological manifestations of the processes that you outlined? For example, in one model you showed that at the craton boundaries, a very rapid change from compressional to extensional fields. I was wondering what would be the geological manifestation of that. Second thing, you also showed, for example, the lithospheric thinning in Indian plate took 65 million years. In North China craton took 28 to 30 million years. What will be the geological manifestations? Would we have surface rifting or volcanism? And my third question, sorry about that, is how does your model explain rifting, the major rifting, for example, rifting of Pangaea or rifting of Gondwana land? If you look at India, you have Singhbum cratons and Dharwar cratons, and on Australia, you have Western Australian cratons and Pilbara cratons. They could have been part of the same craton also. So in your model, can the cratons be rifted, or the rifting will always take place along mobile belt between the cratons? That's all. Thank you.
Well, thank you for your questions. A lot of questions. I'll start from the first. Probably you said that in the age it turned from compression to extension. I believe you said outward, but inwardly, like I would say extension to compression within the cratons. Yes, the geological manifestation is that it's very difficult to say because no geologist has measured the stress of the craton at 100 kilometer depth. So we do not know, but we do see some processes which might be interesting, like maybe some ore formation. I don't know, or maybe if our hypothesis is right, then we'll see that the cratons can increase their thickness over the time. So this could be some manifestation, because geology doesn't work at, there is no way to measure the stresses at 100 kilometers or 300 kilometers. So I don't think that this can be geologically proven or disproven. So we have to rely on the numerical modeling only. The second question was something related to what is the implications of the craton thinning geologically. I mean, this is quite well known. For the North China, when the craton got destroyed, this part got submerged under the water because craton destruction pulled the surface down, and that's why this Japan Sea intruded here. So there's a lower dynamic topography. There are a lot of carbonatite magmatism in this area. So there are various geological implications. And if you have something specific that you are looking for, I don't know. So there are very, very well-known geological implications for this. Recently, people are also saying that because North China craton destroyed, that released a lot of carbon dioxide that lead to the Cretaceous global warming. That is another geological implication. For India, the implication is the Deccan Trap. That is the biggest implication to my understanding. And
But in case of Deccan Trap, for example, your model shows that thinning took place over 65 million years, whereas the Deccan volcanism, they almost all of it came out within a duration of maybe a million years or so.
yes, but this is well resolved in tomography that you see the temperature anomaly is still there. So the heat is there, and as long as the heat is there, you can weaken a craton. So I mean, I do not have this tomography section just right now, but if you just see the tomography section, there are a lot of papers and tomographies will show you that from Africa to India, the trail of the plume is still there. So it's still quite hot region. Yeah.
But Jyotirmoy, tomography does not talk about temperature, right? I mean, I'm sorry, you are going somewhere wrong. Tomography never tells you about temperature.
Oh, I do have a temperature anomaly. Actually, this plume is at...
Yeah, but you could have an anomaly, no problem. But tomography does not tell you about temperature, that's for sure.
Yeah, that's true. But
be correct in stating statements. Okay, thank you.
Right. It shows a velocity anomaly, lower velocity anomaly, right?
So
Yes.
if the plume is still there, the heat is still continuing, but then why we get all volcanism within 1 million year and the next 64 million years we don't see any volcanism?
No, I'm not saying the plume is there. I'm saying the thermal anomaly is there, probably. I don't know how to interpret that. It's a velocity anomaly. We do interpret as a thermal anomaly as well. And the plume is a instability that requires a lot of conditions to fulfill for the rise of the plume. So, I mean, we have the African super plume and the Pacific super plume sitting at the base of the core mantle boundary, as much as the community agrees on that point, but doesn't mean that we are seeing a plume eruption every now and then from them. So something happens, I mean, it will need to fulfill the condition for the upwelling as well.
Okay, thanks.
Thank you.
Any more questions? Yes, Shantanuda, go ahead, please.
Yeah, hi Jyotirmoy.
Hi.
Nice to hear from you again. I'm sorry for stopping you somewhere. You were saying something wrong. Okay, so I mean, well, let's start from the very beginning.
Yes.
I mean, it's good that you're dealing with these large problems, and it is important. We need to know and understand this, even if we understand by parts or a little bit. It's important. So let's start from the basics. I teach this, and I'm sure there are many here who also teach here. So what is the difference between crust, lithosphere, craton, and shield? You have used these four terms throughout your talk, but you mostly restricted yourself on craton. If you can clarify this, then I can go on the next questions, because I really don't know the difference between craton and shield, but maybe there are. So because you are working on that, please let us know. You must be an expert.
Well, yes, to clarify, whatever I've said about the craton is lithosphere. I didn't talk about the crust actually. So everything, whatever I've talked is the cratonic lithosphere. So yes, I should have clarified that. The crust is the upper chemical boundary layer. The lithosphere is the rheological boundary layer. Shield is a term that I've often heard, but I've never used by myself. So I don't know. It's probably, there's another associated term that I used to read in school geography. It's called platform. I don't know what is the difference between the shield and platform, because probably something is exposed, something is not exposed, depending on that people. But yeah, geologically, craton is the Archean lithosphere that I was talking about.
So craton is lithosphere. That's okay. I partially agree. But in that case, in one of your models, you said that because craton has a felsic composition, and therefore it is lighter, and therefore delamination should occur. That is not then valid, because crust has chemical boundary, craton does not. So at the bottom of the craton, or bottom of the lithosphere, you actually have mantle rocks, and these are not lighter rocks.
Yes, absolutely. I said that this is the hypothesis by Thomas Jordan, not my hypothesis, but we are not bothered about density. So in fact, my density is quite higher than the crustal rocks. So
I saw that.
Yes,
I saw that. And that actually brought me to the next question. What is the difference between hydroweakening and thermal weakening? How do you phenomenologically differentiate that? Or how your model is working on that? How are you defining the conditions for this?
Thermal weakening is very simple, actually. So thermal weakening is whenever you vary this E parameter, which is coming from this Arrhenius equation. This is activation energy, basically. So it will have so E plus PV by RT. So if we change the temperature, this E will be adjusted, and it will simply reduce the viscosity. So that's how the model works. About the hydro weakening, sorry.
No. It's not. It's not like. So E term is an energy. This is not an energy here. This is not an energy here. This is derived from the activation energy. This is a non-dimensional form. Okay, what is that?
So this is derived from this whole Arrhenius equation. This is a non-dimensionalized form. So if this E value is, so I know how this balances. So if E value is like 10, then for 100 degree or so if the E value is 10, then around 500 degree anomalies will reduce the viscosity to 10 times. If E is 5, then this viscosity reduction.
Jyotirmoy, don't go into that. Don't go into that. These are jugglery. These are fine. But I want to know what is this E. I mean, I want to know physically what is thermal weakening. You don't say that if E value goes to 10 to the power minus 40, then it is like this. No. And what is thermal weakening? That it will reduce the thickness of the crust.
If you
what is thermal weakening, or what is hydro weakening that you are talking about?
So if you increase the temperature, the viscosity is supposed to go down because of its temperature dependence.
That's correct. But your equation, you don't have to bring that equation to that. If you increase temperature, the strength of the rock would decrease. I mean, for that, you don't have to use that equation. I mean, there are simpler equations.
I'm not sure then what you are exactly looking for. Like, this is a pretty standard phenomenon. If you increase the temperature, it will drop down.
Of course. Yeah. But why the thickness would decrease then? I mean, because of that weakening, why the crustal thickness would decrease?
No. Because of the weakening, it becomes weaker. So then the mechanical erosion will be more. So that will weak the that will erode the.
Where it will go after the erosion?
No,
it's happening at 120 kilometers. Where it will go after the erosion?
Sorry, I think a little bit hearing less, but the weakening is not.
So you are eroding a mass from the bottom of your craton.
Yes.
Right? Where the mass will go and rest.
Where the mass is
eroding, right? You are eroding, right? So you're taking it apart. Where it will go?
So this is an interesting question. This has been asked by some other people also. So we are trying to find out that where this must go. So it's a bit different research question. At this current moment, whatever our models do, that it mixes with the mantle.
Do you see a geochemical signature for that? I asked you this question a long time back. Do you see a geochemical signature for that?
Well, are in fact, so there is no very specific geochemical signatures, but people do get some old Archean continents in the middle of Indian Ocean.
Archean continents, not mantles.
Piece of the
Because they
micro.
should mix with the mantle.
Yes. So we had discussion about those people who actually found those small piece of Archean continent from nowhere in the oceanic crust, and they were curious to know, like, if it has something to do with the craton destruction. So we don't know. That's a research question. We don't know where do they go.
So how does your mass balance is working then in your numerical model?
Here we do not have a chemical heterogeneity, so it treats everything as same. There is no for this particular model there is no separate phases or chemistry here. So this only solves for we identify craton just as a viscosity parameter.
Okay, I mean, I have many more questions because I mean these are things where actually we should look more and work. And please don't take my questions as I mean, I'm afraid of nowadays asking questions, but I know you, so it's just
If you have more
to
questions,
discuss.
just drop me an email. I'll
Yeah, just to discuss. And one more important thing that you said, that Hooke's law is stress is proportional to strain rate. He said it. Hooke's never said this, so correct it. It's Newtonian rheology. So yeah, just that part. But good talk. Thank you. Okay. Good.
Nilanjanda, go ahead, please.
Okay. Can you hear me, Jyotirmoy?
Yes, sir.
Jyotirmoy, I must congratulate you for a very well-structured talk.
Thank you, sir.
Now, as Professor Mishra also said, I also teach a little bit of it to the master students, so I have little idea about it. But mostly, my question revolves on whatever you have showed is from around 500 million years onwards, if I got it correctly.
Right, 410 to be very specific. Like these global models are from 410.
410, fine.
Yes.
So where you have constrained the dimensions of the present day cratons, and then you have tried to show that yes, with this amount of viscosity or whatever, they would come to their present state. Now
Yes.
my question is, like, this lithosphere has changed in composition and depth from Archean till this 409. So do your models like your I mean your conclusion that 25 million years they lose 50% of their volume. So do your conclusions drawn from a small time span, which is almost 1/10 of the total time span of the Earth, conform in older days too, or there would be something different? Because as the cratons evolved, the lithosphere also evolved, as I can understand.
Yes. So we do not have this chemical evolution here. So that's a limitation of the model. That's why I actually gave a introduction of the modeling. Like, we cannot go to the reality, so we have to use the most optimized ones. So there is I don't know if there is any numerical model that can handle the cratons, all the chemical evolution also. I mean, of course they can handle, then they cannot probably handle this long-term dynamics. So but we are trying to develop. So at a single go we cannot answer all the questions, but it's a relevant and very interesting question for the geologists, that how these models take care of lithospheric or crustal evolution. The answer is no. We cannot track the evolution of the chemistry or the geology of the cratons in this model. There is no. It's the only thing that we can track here, the physical property, that is viscosity. Yes.
Yeah, so the physical property also deals with the thickness of the craton.
Yes.
And also, even if you remove the chemical aspect of it, the ambient mantle temperature, which is very important, which was quite high during the earlier days than the time frame that you have worked upon, do they really, according to your view, do they really influence the your model, or your model has to be refined?
Yes, of course, there is always chance to refine the model. So there's no ultimate model. So these models were done when I just learned this, and then whatever you pointed is very specific. Yes, the ambient mantle temperature is constant in these models. So now I know some of the models where the mantle ambient temperature, the mantle potential temperature can change, but in this model it is fixed at certain values. I think around 1400 degrees centigrade. So it did not change, and I do believe that yes, that can change the dynamics.
Yeah, because
That's
the,
why-
the portions of the Earth that you took in your model, they have been long standing for quite almost 3.5 billion years. So
Yes.
they are stable. I mean, it's no point that they would be unstable after 409. But
Right.
whatever their stability, instability, that must have happened long back. That was intriguing me, as you are working with something which is already stable, which has already stabilized.
Yes.
Any
Yes.
oceanic islands which had formed during this time, which could have suffered destabilization, that would be more interesting between this time frame, where we for sure we know plate tectonics works. And if we go back, as you started your talk, as you go back, there are different mechanisms,
Yes.
which there are different schools of thoughts, and they are always competing against each other, and we do not know for sure as to which model would be valid in those times. So nice talk, fine, but I think a little bit of, as Shantanu, Professor Misro has also pointed out, like uh, a little bit of chemical affinity, little bit of more physical parameters, and putting it back a little more would be very nice to hear. I am sure you will do that in future, and I look forward to that.
Thank you, sir.
Thank you. Thank you.
Thank you, Nilanjanda. Any more question? Yes, Handullah, go ahead.
Yeah, I must. I just wanted to tell Jyotirmoy that it was an excellent talk.
Thank
And
you,
of
sir.
course, we need to take care many things while modeling. We all know that. So I am sure Jyotirmoy will take care of that in his work in the future. And I think he has really targeted a very important item that we need to work on. We need to understand how this continental lithosphere evolved, and they are stable for so long time. In the meantime, I just wanted to clarify myself, Jyotirmoy, that you showed the flat slab subduction. That
Yes.
is the subduction of the oceanic slab or continental slab?
Yeah, it's an oceanic slab. This is the actually Paleo-Pacific slab.
So here is the question: how do you explain flat slab subduction for the oceanic slab? Because all the subduction model that I have seen, or I know little, that you cannot have this flat subduction like this. What you can interpret now the Indian slab beneath the Tibet.
Well, we had to start from somewhere. So this interpretation of the flat slab is not mine, but I can show at least 10 papers which are talking about this, like 10 big papers, not some.
No, I understand. The big paper, small paper, I don't want to quantify like that. But from mechanical point of view, I really don't understand how you can have flat slab subduction. What could be the setting, and what could be the boundary condition where you can have flat slab part of the subducting slab of the oceanic subducting slab?
Yeah,
That is
so
not clear to me, at least. That's what I want to know, because it's very.
I believe there are many theories and hypotheses on how the slabs can be
Because
flat.
nowadays, Jyotirmoy, if you look at the tomography image, you will
Yes.
see that the inclination of the slab, average inclination of the slab is 45 degree.
Mhm.
And the minimum inclination is 30 degree. You cannot have, if you look at that now, at least in the global scenario, you have 28 active subduction zone, and the length of this active subduction zone is 52,000 kilometers in today's state. But nowhere I have seen that there is a flat slab subduction. This is the
Well-
most. That's what my question is. How we can start from a thing which is not really, we cannot see it in today's global scenario. This is just a question. Just a
Yeah,
question.
that's an important question. And
One thing could be like that, because maybe this is the very hot. It should be very warm slab. It should be buoyant, and that has to be like that. Do you think that very warm slab will subduct?
yeah, but
I really do not know.
yeah, I don't know really. It might be, it can be like, it's warm, it's in an intermediate density between the continent and the mantle, so that might get flattened.
No,
There is-
that is okay. Flattened slab is fine, but in fact, I don't know. I need to look into it, and I need to think on it. If it would have been a continental subducting slab, I have no problem, no issue. But for the oceanic slab, I really do not know. You are working with Thorsten, and you can also talk to him regarding this.
This work
Maybe-
was not actually the Thorsten, but yeah, definitely I can ask him. Yeah.
And another thing is that there must be some forces from the bottom up forces that can really lowers the inclination of the slab. And what is the force? That could be some plume as well. So at some specific situation, it can happen like that. This is just an idea.
Yeah. I think some people have talked about this dynamic pressure. Probably that can also be, but I don't know. Yeah, that's a completely different research question. It's a very important research question, I do believe. Yeah.
Otherwise, Jyotirmoy, it's a fantastic talk, and there are some weak planes are there, of course, and when we need to really work on it, and I'm sure you will do that, as Professor Mishra also said, Professor Dasgupta said. Okay, so I hope we will hear you again with your new data set that you are coming up in your next topic. Okay, thank you very much, Jyotirmoy.
Thank you, sir.
So Jyotirmoy, there is a question in the chat box from Aishwarya. Can you answer that if you can read it?
You have shown that due to the self-compression, craton will have a shorter width and thickness will increase. So, for the isostatic equilibrium, we need a deeper root, but you have shown that the lower part of the craton will get eroded. Oh, I think, yeah, that's an interesting question, but I think what Professor Mishra was asking, that might resolve your question by this time, because isostatic equilibrium is a crustal phenomena, and what I talked about is completely, it's a lithospheric adjustment. So we are not talking about the isostatic equilibrium at any point here. So yeah, deeper root will not destroy or change anything with the isostasy.
Okay, any other question? Another question. What do you exactly mean by Indian craton?
Well, that's a tricky and interesting question. What I do here, I would say this is simply the Dharwad craton. In this particular model, this is just the Dharwad craton.
In fact, in your diagram, what I have seen in your map, only the Dharwad craton is the stable part, as you said, right?
Yes,
From the
because
model.
these are taken from the seismic tomography. There are a lot of controversies on the Indian craton thickness, and they do not. Seismic tomography probably cannot resolve the exact geometry.
Yeah.
So in one of my recent model, I started drawing from the geology, I mean geological boundary. But yeah, these are the old works, so it still has the Dharwad Craton only.
Okay. Okay.
Well, I mean,
Well,
Jyotirmoy, Shantanu again. Yeah.
Yes.
So if you look at some recent works of Shamsundar Rai and his co-workers, they actually came up with significant high-resolution tomographic data of different parts of Indian Craton, including Dharwad. He actually separated western and eastern Dharwad very recently. He showed thinning happening towards the western part, and he also explained a lot of things out of it. So, I mean, I would expect when you show these things, particularly when you're and this is also for South China Craton, valid for South China Craton. There are a lot of tomographic data. So, I mean, I would expect some at least references of tomography to support your model in your presentation. That would be actually good to see that it is happening. So it is there. And one more suggestion that there could be many papers who say XYZ. That doesn't mean that XYZ statements are right. We question them. That's why we are scientists. That's why we progress with that. I mean, there are nature papers that say that Tibet is subducting under Indian plate, and this got published in Nature even. So that doesn't mean that we have to accept it and we have to consider it. This is right, and then we have to make our models that way.
Yeah.
Anyway, I mean, I must say that, I mean, you see that this is one of the talks in recent pasts where we had a lot of discussions. So you probably are doing or hitting the right question.
Yeah.
Thank you.
You're doing very good.
Thank
You're doing very good. And at least I found a lot of interest in it.
Thank you.
Okay, if there are no further questions,
Just I mean,
go ahead.
really, Jyotirmoy, I also learned a lot. But one thing, there is a paper by Jim Baker. It's a very old paper. He was basically a geomorphologist. I would like to share. Now, you will find that reference in Anderson and Anderson's book of active geomorphology, and it says that there is a direct link between the areal extent and the time that particular geomorphic region survives. So for cratons and continents, it's in the order. I mean, he has listed out from cratons to a small ripple in a small rivulet. So this is the dimension, and this dimension varies in the order of 10 to the power, from 15 to 10 to the power 7 square kilometers, more than 10 to the power 9 square kilometers, to 10 to the power minus 4 square kilometers, something like that. And the age, it varies in terms of billions of years. So I was just wondering, I mean, in fact, when I got the message of Jyotirmoy's lecture, I was wondering, this would be very nice to hear. And I'm really glad, Jyotirmoy, you're working on such things. But also, there are many dimensions of this, of this problem. So I am eager to hear you on those dimensions later on as well. So carry on the good work.
Yeah, thank you.
Any more suggestion, comments? Sumita is there. Sumita is there or not?
Yes.
Sumita, are you there?
Yes, I was listening, and very stimulating and very detailed discussions that followed. Yes, it's very, very.
Your
very
suggestion may help to Jyotirmoy to think further, Sumita. If you have any suggestion.
I don't have anything else, but other than congratulating him for the excellent work and the questions it provoked that reflects the significance of his work. Okay.
Thank
Thank
you
you,
so
sir.
much. Jyotirmoy,
Yes.
Moldik.
Yeah.
Sorry. So
Yeah,
if
so I
you
think,
have any more queries, suggestions, then we can give a big round of applause to Jyotirmoy Paul.
Yes. Yes. Very well done.
So, okay
Yeah.
then.
We
You
can
can
close the
conclude the
session
session.
now, and then I will notify you with the next talk for June. Thank you
I'll have
very
to
much.
read this paper, Paul et al. 2023. I
Yes,
missed
sure.
it.
It's open access. I can send you the link.
Okay, that would be great, Jyotirmoy.
Yeah.
Yeah. Okay. Thanks.
Thank you.
Okay.
Okay.
Everyone in Kolkata, please take care. I hope the worst is over. But yeah.
Yeah. Now it is in the declining mode.
Very
Okay.
comfortable now.
Yeah. It's comfortable. But you don't go to College Street.
Me and
Don't go
Shantanu fled from College Street today at 2 o'clock. It was already near knee-deep water.
Yeah.
Why did you have to go to work today? You could take a break today, Nilanjanda.
Nah, I mean, taking a break and staying at home is more arduous than going to college. But as it transpired, that for today was more arduous.
I think everybody will really agree with you.
So we had a nice tiffin. We took khichdi and all, and then we decided that enough is enough. Before it grows, the water becomes much deeper. We have to leave because we both were driving, and we had to drive back rather. So we just came through.
Good. Adventurous geologists. Good.
Yeah, yes.
Okay.
Okay.
All right.
Before
Take
our
care.
car gets abducted, we want
Yeah.
to.
Into the thin slab of Kolkata. So, yeah. All right,
Tata.
everyone.
Okay, Tata.
Bye.
Tata, bye bye.
Everyone. Yes, yes. Bye.
Tata. Take care.